Okay, so for our last section, we're going to be talking about advanced nuclear reactors. So all I need you to do for this section is to be able to explain the fast neutron reactors and how fusion reactors work. So first one we're talking about is a breeder reactor, and this is kind of a lot. So instead, I'm going to try to use pictures first. And the first picture is going to be this one right here. So if you remember back from last section, we have uranium-235, and that goes through fission. So we break it apart. We make the halves. Sometimes it's cesium, sometimes it's rubidium. Doesn't really matter. What does matter is that neutrons will fly off of it, and that is kind of the whole idea. Remember the chain reaction, we want the dominoes to get bigger and bigger and bigger to waste more and more energy. This neutron is going to go on and hit another uranium atom, hopefully to cause another chain reaction. Sometimes though, the uranium isn't going to be the 235, the fissile variant. It's going to be 238. And this is explaining how we get to nuclear energy as a renewable energy. So instead of splitting uranium-238, sometimes the neutron is captured by it. And that will set off a really neat sequence of events where you get a different isotope of uranium called uranium-239, has that extra neutron here. And then even cooler is that it like trades a neutron for a proton and becomes this other substance called neptunium. Neptunium has 93 protons to uranium's 92, but 146 neutrons. Give it a little more time and it degrades into this thing called plutonium-239. So it gains another proton and loses another neutron, right? So uranium-238 becomes uranium-239, becomes neptunium-239, becomes plutonium-239. And this is the good stuff, right? This has a lot of energy within it, even more than uranium. So when we say nuclear energy is renewable, what we mean by that is from the byproducts of uranium-238 and uranium-235 fission, we get this plutonium-239, and then we can use that for fission as well. So hopefully all that is explained right here. The most important figure is that you take the non-fissile uranium-238 and turn it into fissionable plutonium-239. And the general increase in fuel is 100 times the amount, not 100%, 100 times. So it's a lot more energy. And that is, of course, reprocessing. We have lots of uranium, so we have enough stockpile to do as much nuclear energy processing as we want. The world supply isn't a problem at all because of all the decommissioning from last section. We learned about how nuclear bombs and nuclear power plants can use the same fuel as long as you lower the ratio of uranium-235 to uranium-238. And we can also use this thing called mixed oxide or MOX fuel, and that can be used in power plants as well to create steam and turn the turbines. Now, the next kind of reaction we're going to talk about is a fusion reaction. So if you remember, fusion is exactly what it sounds like. It is the fusion of two or more atoms together. And this comes from, or is inspired by how stars work. So stars get their energy from fusion, and that's a lot of energy. Just think about the sun. It's not a particularly large star, but it makes all the light we see. It gives us all the heat that we feel. So it is a big energy source, right? So the way you do it is to take different isotopes here. So this is deuterium here, and this is tritium here. And these are isotopes of hydrogen. So the deuterium is going to have extra neutrons, and the tritium is going to have even more extra neutrons. When you smack them together really quick, you get this unstable helium atom, right? So it's got the 2 protons and 3 neutrons. Well, it doesn't like that. So it's going to decay into a regular plain old helium. It's not radioactive, and a neutron, and in the result make energy both directly and indirectly, as the neutron is going very fast and contains lots of energy of its own. So we use that technology mostly to make it as a bomb for warfare. Why is that? Well, it's because the deuterium-tritium reaction, or the DT reaction for short, isn't energetically favorable yet. So we haven't figured out a way that the reaction makes more energy than it consumes. So right now it's just not worth it, right? We can get deuterium pretty easily. It's pretty readily found just in water that's in the ocean, but tritium has to be artificially produced. That takes a lot of energy. It's very radioactive, it's gaseous, so it's hard to control. There are plans to make it more sustainable. So the International Thermonuclear Experiment Reactor in France, which if you remember has or gets all of their energy from nuclear power plant electricity, it's $11 billion with a whole new design, and the thought is that it creates 10 times the amount of power it consumes, and that's a very, very good ratio. Imagine I don't know, investing $1 and getting $10 back, and then investing $10 and getting $100 back. That's a really good rate of return. So I haven't seen it yet, but we're hopeful, and that'll be really good because that is a lot of energy to get from it. Okay, so as review, just want you to tell me about the two kinds of reactors. That'd be the fast neutron or the breeder reactor, and the fusion reactor, aka the DT reaction, aka the deuterium tritium reactions. So as always, go ahead and if you have any questions, email me or post to the Google Classroom forum. And thanks for watching. Talk to you guys later.